Hello students. In this video, we'll be talking about the subtopics of molecularity, order, and rate equation. These subtopics come under the AHL section of the unit Chemical Kinetics. So, I'm sure that you are aware that chemical reactions can be classified in a number of ways. For example, they can be classified as exothermic or endothermic depending on whether they release energy or they absorb energy. Now, another way to classify chemical reactions is based on the number of steps which occur. For example, here you can see on the left side we have a reaction involving silver ion in the aqueous solution reacting with chloride ion in the aqueous solution to make a white precipitate of silver chloride. Now, this reaction occurs in a single step. Such reactions which occur in a single step are called elementary reactions. However, on the right side, you can see another chemical reaction. This chemical reaction under low temperature, as you can see in the image, occurs in two steps. So the net reaction is this one, but this reaction occurs in two distinct steps. Such chemical reactions which occur in two or more steps are considered as complex reactions. In a sense, you can say that a complex reaction is made up of two or more elementary reactions. So when talking about elementary reactions, we come across the concept of molecularity. So what is molecularity? Molecularity refers to the number of reactant particles, which may be atoms, molecules, or ions, that are colliding simultaneously to form the product. Okay, so the important term here is that they are colliding with each other simultaneously in an elementary step. So depending upon the number of reactant particles participating in an elementary step, we have broadly speaking three kinds of reactions. So first one is a unimolecular reaction where a single reactant splits into products. As you can guess, these reactions are primarily decomposition reactions. Then you have bimolecular reactions where you have two reactant particles colliding with each other to form products. So you can have A plus B giving products, or you can have A plus another A giving product. So even if two identical particles are colliding with each other, that also falls under the domain of bimolecular reaction. Then we have third molecular reaction where we have three reactant particles colliding with each other simultaneously to form products. Now, third molecular reactions are quite rare, and perhaps you can understand why. It's because it's very difficult for three reactant particles to collide with each other at the right orientation and with energy more than or equal to activation energy to form a product. The probability of that happening is quite low. Still, pure molecular reactions do happen, but they are quite rare. Now, here are some examples of unimolecular, bimolecular, and termolecular reaction. As you can guess, if you just add up the coefficients on the reactant side, you kind of get the molecularity of that particular reaction. Please note that molecularity is only defined for elementary reactions. Now, how do we experimentally determine the effect of concentration of reactant on the rate of reaction? Perhaps a number of times we have discussed that increasing the concentration of a reactant increases the rate of reaction. But does that happen every time? And if it does happen, does it happen to the same extent? So here we'll attempt to answer this question using the terms order and rate equations. Now here we have a hypothetical chemical reaction where reactant A is combining with reactant B to make reactant C. And here are three trials or experiments which are being conducted. with different relative concentrations of A and B, and the rate of reaction was measured. Initial rate refers to the rate of a reaction when it just initiates. So that means rate at time t equal to 0. Now, in the first set of experiments, you can see that when the concentration of A and B were taken as 1 mole per dm cube each, the initial rate was found to be 2 moles per dm cube second inverse. Please don't misinterpret this information as 1 plus 1 equals 2. So these three quantities are independent of each other, and this is an experimentally determined rate, not determined theoretically. In the second experiment, we can see that the concentration of B is kept the same, but the concentration of A is doubled. So essentially, all the reaction conditions were kept same except for the molar concentration of A, and the initial rate was measured again. And here you can clearly observe that the initial rate remained the same. So you can just pause the video here for a minute and try to answer this question. What has happened in the context of rate of reaction when the concentration of A was doubled? Well, as you can clearly see, the initial rate remained unchanged. Now, as to why this happens, we'll talk about that when we are discussing about mechanism of complex reaction. But here, the takeaway is that in the context of this hypothetical chemical reaction and this data, we can say that rate is proportional to molar concentration of A raised to the power 0, which we know is 1. Basically, it means that the rate of this specific reaction is independent of the initial concentration of A. So even if you make it 10 times, the rate would remain unchanged. Again, the answer or the reasoning to this specific question as to why this happens comes later. Now let's see what happens in the third experiment. In the third experiment, you can see that the concentration of A remained the same as it was in the first experiment, and the concentration of B was doubled. And here you can see what is happening to the rate. I want you to pause the video here and try to answer the second question as to what is happening to the rate of reaction when the concentration of B is doubled. So if you concluded that the initial rate doubled as the concentration of B was doubled, then your conclusion is absolutely right. So here you can say that rate of this specific reaction is directly proportional to the molar concentration of B raised to the power of 1, which means that if the concentration of B was made 10 times, then the rate would also become 10 times. If you have any confusion with respect to the interpretation of this data and the response to these questions, please reach out for me in the class. All right. In order to have a better idea of how the rate depends on the concentrations of reactants in different ways, let's take another hypothetical example. So here you have the two reactants D and E, and they are giving rise to a product that's F. And here you can see we have the three experiments, and we have different concentrations of D and E in the first experiment, and the rate of the reaction was found to be 6 moles dm inverse cubed second inverse. Now you can see what is happening between experiment 1 and 2. The concentration of E was kept the same, whereas the concentration of D was doubled. Now, look at the effect of doubling the concentration of D on the initial rate. I would like you to again pause the video and try to establish a correlation between the initial rate of this specific reaction and the molar concentration of D. Alright, So what we can see is that when the concentration of D is doubled, the rate becomes 4 times. What this essentially means is that the rate in this specific instance is directly proportional to molar concentration of D squared. Okay, so what this means that if we increased the concentration of D by 4 times, the rate would have become 16 times. Okay, so not 8 times but 16 times. If we increase the concentration by say 10 times, the new rate would become 100 times the original rate. Okay, so here you can say that rate of this specific reaction is proportional to molar concentration of D raised to the power 2. Now, if you compare experiment 1 and 3, you can perhaps also reach a conclusion, correlating the relation between molar concentration of E and the initial rate. I would like you to pause the video here for a moment in order to answer that yourself. Alright, if you have given it some thought, perhaps you have identified that here, even when we doubled the concentration of E, the rate remained the same. So what this means is that the rate is essentially independent of molar concentration of E. So we can say, in other words, mathematically, the rate is proportional to E raised to the power 0, which is basically 1. So here we see that it's it's not necessary that the rate depends on the molar concentration of all the reactants involved equally. Sometimes it might be just completely independent of one of the concentrations of the reactants, and at other times it might depend, having a squared relationship instead of a direct relationship. So again, as to why this happened, we'll talk about this later when we talk about reaction mechanisms. So here I introduce the concept of order of a reaction. So what is order of a reaction? In the previous example, you saw that rate was proportional to D raised to the power 2 and rate was proportional to E raised to the power of 0. So the powers that the molar concentration of the reactants are raised, uh, explaining the dependence of the rate of the reaction on the molar concentration. These powers are termed as orders. So orders kind of tell us mathematically the correlation between the rate of a reaction and the molar concentration of the specific reactant. What we saw in the two examples before is that sometimes even if we double the reactant concentration, the rate stays the same. In such cases, which is the case with E over here, in such cases we say that the order with respect to that specific reactant is 0. Alright. Now, if we double a concentration of one of the reactant and the rate also doubles, that means hypothetically speaking, rate is proportional to molar concentration of X raised to the power 1, where let's say X is a reactant, then this 1 becomes the order of the reactant with respect to 1. And lastly, in this previous slide, we saw that doubling the concentration of rate kind of quadruples the rate of the reaction. So in that case, the order of the reaction with respect to D is 2. So this is how the uh, order of reaction with respect to specific reactants is represented. Okay, notice that unlike molecularity, where we were just seeing the coefficients of an elementary reaction and adding them together, order of a reaction has to be determined experimentally. So in order to extend this concept further and to arrive at the concept of rate equation, let's again look at a reaction. G plus H gives I. So I would like you to pause the video here and try to answer these two questions before I go into the details. Right. So we can see from experiment 1 and 2 that while the concentration of H remained the same, the concentration of G was doubled, and here we can see the rate is also doubled. So basically, rate here is directly proportional to molar concentration of G raised to the power 1. We can also write it as rate is proportional to molar concentration of G, because we know that if nothing is written, it's basically to the power 1. So here the order of the reaction with respect to G is 1. Okay. Now, if we compare experiments 1 and 3, we find that the concentration of G was kept the same, but the concentration of H was doubled, and we see that it had no impact on the initial rate. So the conclusion that can be deduced is that rate here is not dependent on concentration of H. In other words, the order of the reaction with respect to H is 0. So when we talk about the overall order of the reaction, what we do is we basically sum up the individual orders. So let's say you had a reaction X plus Y gives Z, and let's say you arrived at this specific relation after making experimental observation that rate was proportional to X raised to the power M, and rate was proportional to Y raised to the power N. So here M and N are actually orders with respect to X and Y. So if we have to deduce the overall order of the reaction, what we need to do is we just need to sum the powers. So in case the values of M and N are 2 and 1, this becomes a third order reaction by just summing up 2 and 1. If the powers were 1 each, the sum of the two becomes 2. So it's the overall order of the reaction is 2. If you had the rate something like independent of the concentration of X but directly proportional to Y, then the overall order becomes 1. And if we had a law stating that it was independent of the concentration of X but dependent on the concentration of Y raised to the power 2, the overall order again became 2. So you can see here that there are a number of ways to get an overall order. The overall order is deduced from the individual orders, but if you just know the overall order, you actually can't make out what the individual orders are. You have to go back to the experimental data to arrive at what the individual orders are. So again, just to apply our understanding gained so far, I'd like you to pause the video and answer the three questions after making observations in experiment 1, 2, and 3. Okay, so what do we see here? So if we see the difference between experiment 1 and 2, so here the molar concentration of J was doubled, the concentration of K was kept constant, and we saw that the rate was also doubled. So in this case, we can safely say that rate is directly proportional to molar concentration of J raised to the power 1. In other words, the order of the reaction with respect to J is 1. Similarly, if we look at experiment 1 and 3, we see that the concentration of J was kept the same, but the concentration of K was doubled and the rate remained the same. So again, rate is independent of the concentration of K. In other words, it's the order with respect to K is 0. So what will be the overall order of the reaction? If we had to combine these two, it would look something like rate is proportional to J raised to the power 1 times molar concentration of K raised to the power 0. So the sum of the orders becomes the overall order of the reaction, which is 1. Just to reinforce the understanding again, here is another example. M plus N gives O. I'd like you to pause the video and try to answer the questions. Alright, so here if we see the data of experiments 1 and 2, we see that the concentration of N was doubled while keeping the concentration of m constant, and we saw a quadruple jump in the initial rate. So we have seen earlier that if we double the concentration of a reactant and if the rate quadruples, that means there is a squared relationship between the rate and the molar concentration. So here we can safely say that rate is proportional to molar concentration of N raised to the power of 2. So the order of the reaction with respect to N is 2. Now, if we look at experiment 1 and experiment 3, here we find that the concentration of N was kept constant, but the concentration of M was doubled. And when the concentration of M was doubled, the rate also doubled. So here it's a direct proportional relationship. So we can say that rate is proportional to M raised to the power 1. So the order with respect to M becomes 1. So if we combine these two, we have the expression rate is proportional to molar concentration of M raised to the power 1 times molar concentration of N raised to the power 2. And if we combine the powers, the overall order of the reaction becomes 3. So this is a third order reaction. Now, if we need to get rid of the proportionality sign, we need a constant. Similarly, in context of rate, in order to remove the proportionality as mentioned in the previous slide, we need to have a constant, and that constant is called as the rate constant, which is k. Not to be confused with the equilibrium constant, which is symbolized by uppercase k. Okay, so rate constant is represented by lowercase k, and rate constant is the proportionality constant that we insert in a rate equation. So a rate equation, it tells us how the rate of a reaction depends on the molar concentration of the constituent reactants. So here you can clearly see that the reactants we are talking about are A and B, and M and N are the orders with respect to A and B, and K is just the proportionality constant. So rate constant is essentially telling us about how fast or slow a reactant is. So the faster a reaction happens, the higher is the value of K. And just like the equilibrium constant, the rate constant of a reaction also solely depends on temperature. It doesn't depend upon the concentrations of the constituent reactants. So I hope the idea of orders, rate equation, and rate, molecularity, those are clear to you. So rate constant necessarily doesn't have the same unit. Why? Because just imagine a reaction. Rate always has the units moles dm inverse cubed second inverse, right? And let's suppose you have a reaction which says molar concentration of A raised to the power 1 and B raised to the power 0. In this scenario specifically, this particular term won't have any unit, whereas because here molar concentration of K is raised to the power 1, this would imply that the units here are moles dm inverse cubed. So what would be the unit of K here? The unit of K would be rate, which is mole dm inverse cubed second inverse, over the molar concentration of A, which would just be mole dm inverse cubed. So here the unit would just be second inverse, or essentially any appropriate unit of time inversed. Now let's imagine another scenario where the orders with respect to both A and B were 1. So in such a scenario, we have we have a square of the molar concentration. So that would basically mean mole squared dm inverse raised to the power minus 6. And on this side, we still have mole dm inverse cubed second inverse. So if we now try to arrive at the unit of rate constant, that would be mole dm inverse cubed or second inverse over mole squared dm inverse raised to the power minus 6. So here the unit of the rate constant would be mole inverse dm cubed second inverse. All right, and that's what you see over here. I would like you to give it a try and try to arrive at the unit of the rate constant for a third order reaction. These are the final units that you will eventually arrive at, but it would be good if you try that on your own. So to sum up, this table kind of compares the essential differences between molecularity and order. We saw that molecularity is a theoretical concept which is arrived at by just adding the number of reactant species which are colliding simultaneously in an elementary reaction, whereas order referred to the sum of the power of the concentration terms in the rate equation. Molecularity, since the number of reactant particles cannot be fractional, it can only have integral values, whole number values, whereas order can have fractional values as well. Just to give an example how a fractional order is possible, imagine a scenario where you had, if you increase the molar concentration of reactant 4 times, the rate became twice the original concentration. So here you can see that there is a positive correlation, but it's not a directly proportional relationship. It's not a squared relationship. In fact, it is rate is proportional to the concentration of A raised to the power 1 by 2 here. So this proves that order can have fractional values also. And in some of the cases, as we saw in a few examples, the order can be zero as well. Whereas molecularity of a reaction cannot be zero because some or the other reactant has to be involved in order to make products. So here I would like you to pause the video and try to answer this question yourself. This is a past paper question. What would be the units of the rate constant if the rate equation is rate equals K times molar concentration of A times molar concentration of B squared? So if you arrived at the answer C, you got it right. I think you can go back to the previous slide where we talked about the how to get the units of rate constant. So I hope this explanation of molecularity, order, and rate equation was clear. We'll try to have more advanced exam style questions in the upcoming tutorial. Thank you so much.